In this class, we will be working with a lot of terms or factors that have this form. What is this? Well, b is called the base, and we're going to be using them as variables for now, most notably x, and p is the power. So just an exponential expression or an exponential factor. The powers are going to be numbers for now. We will look at these when they're flipped, but for now, just bases are variables, powers are numbers. B to the power of p is the same thing as b times b times b. Keep multiplying them for a total of p times. For x to the fifth times x cubed over x squared, I can rewrite this as x to the fifth is just x times x times x times x times x. It's 5 of them. Times x cubed, which is x times x times x, all over x squared, which is x times x. Of course, this is just multiplying. Everything's multiplying here, so I can rewrite this as x, 2, 3, 4, 5, 6, 7, 8, all over 2 in the bottom. And at this point, you can see, well, I can cancel out a common factor of x. That leaves me with, of course, 1, 2, 3, 4, 5, 6, which is the same thing as x to the 6th. And x to the 6th is way better, way more useful, way easier to use than this first expression of x to the 5th times x cubed over x squared. Now, this is a simplistic problem, and we can use just the expansion of the base to solve it. But for more difficult ones that require, that have a lot more in it, it can be helpful to have some rules that we can use. The first rule we're going to be looking at is called the product rule. And this says that two exponential expressions that have like bases, so b is the same in both of these, with the same or different powers, it doesn't matter. This is the same thing as adding the powers. So you can change two of them into one with just the addition of the powers. Multiplying leads to addition of the powers. Okay, so I have this expression here, and I'm going to rearrange it first so that the numbers are all together and the variables are all together. I can do this because multiplication is commutative, so 3 times 2 is the same thing as 2 times 3. You can just rearrange all of it. Now, of course, 1 times 3 times 20, 1 times 3 times 20 is 60. And we're going to look specifically at these first two, and then we'll look at the resulting in the last one. So x cubed times x to the 5th. If you were to multiply this whole thing out, it's just like in the previous problem that I showed you. X cubed times x to the 5th. There's 3 of them in the first, there's 5 of them in the second. They're all multiplying, so there's going to be 8 total. That's the same thing as saying x to the 3 plus 5. Of course, 3 plus 5 is 8. And now we can take care of the last two, 8 plus 10, and that gives us x to the 18. Of course, I wouldn't do this in this step-by-step process. In the very beginning, I would just look at this and say, well, this has to be 60x to the 3 plus 5 plus 10, which is 60x to the 18. That's really kind of how you should be doing this. Everything that's like bases that are multiplying, just add all the exponents together. Go ahead and try out number 1. Okay, the next rule we're going to be looking at is the quotient rule. So in the previous one, we had like bases that are multiplying, gives us addition of the powers. Here we have like bases that are dividing, and that's going to give us subtraction of the powers. Multiplication goes to addition, division goes to subtraction. Okay, similarly, I'm going to split this thing up over these two things. You can break up a fraction, right? 2 over 5 times 3 over 8 is the same thing as 2 times 3 over 5 times 8. That's just addition of multiplication of fractions. So you can combine them. That means you can also break them up. And this is a little bit easier to think of if you break them up over the kind of like things, so the numbers and the bases. 14 over 35, I can reduce top and bottom by 7. It's going to give me 2 over 5. And here I have a division of like bases, so that's going to lead to subtraction of the exponents. 8 minus 2 is 6. This, of course, is the same thing as 2d to the 6 over 5 in the numerator. Either one's fine, though. It's the same thing because you can write this over 1. But that's what the resulting power is. So here I have like bases. In this case, the number 2 to the 7, that's just a constant. And we could write that out as some large number. It's going to be very, very, very large. So it's actually easier to think of these things as powers of 2 because I can just use a quotient rule to simplify. It's going to be 77 minus 81. And that gives us -4. All right, go ahead and try out number 2. Okay, the next rule is the power rule. Power rule is where we have some base to some power, and that whole thing is to another power. It can be the same power or a different one, doesn't matter. And in this case, this is the same thing as b to the power of m times n. You can think of this as, let's give an example, 2 cubed squared is the same thing as 2 cubed times 2 cubed. But 2 cubed times 2 cubed, that's like bases adding, or sorry, like bases multiplying. So we're going to add the exponents, and we get 2 to the 6, which is the exact same thing as in the original part, just multiplying 3 and 2. That's where this whole thing comes from. It's really just an application of the product rule. So in practice, this is very easy to use. -13 is to the power of 5, and that whole thing is to the power of 7. So this is the same thing as -13 to the power of 5 times 7, which is -13 to the power of 35. Now, this is a great answer. One thing you can note, if you just think about a little bit, how does a negative go to a power of 35? Negative times negative is positive, so even pairs of negatives cancel. As long as they're multiplying, and everything here is multiplying. So this is actually the same thing as -13 to the power of 35, where 13 is the power of 35. The negative comes on the outside, but that's just because it's the same thing as -1. That's just a minor thing, but they're actually both the same expression. Either way, power to a power, multiplying the powers. Go ahead and try it in number 3. All right, zero exponent rule. This says b to the power of 0 equals 1. It's always going to be the case, even with 0 to the 0. There is some controversy about that, but we're going to assume it just equals 1. So 0 to the 0 power, b to the 0 power, anything to the 0 power equals 1. Here I have two like bases multiplying. So I'm going to add the exponents. Plus a -13 is the same thing as minus. So 13 minus 13 is 0. And it doesn't matter what k is. It's always equal to 1. Give it a try in number 4. Okay, so according to the quotient rule, 2 to the 4th power over 2 to the 7th power equals 2 to the 4 minus 7, which is 2 to the -3. Now, by doing the powers and simplifying, so 2 to the 4th power is the same thing as 2 times 2 times 2 times 2. That's 16. 2 to the 7th power is 16 times 2 times 2 times 2, which I believe is 2... No, not 256. It's 128. Okay? And then on top and bottom, I can actually divide both by 16. That's going to give me 1 over 8. So if 2 to the 4th equals 2 to the -3, and 2 to the 4 over 7 equals 1 over 8, it stands to reason that 2 to the -3 equals 1 over 8. And that's actually the same thing as 1 over 2 cubed. And this is what we're going to be really looking at here. So just kind of ignore this 1 over 8 portion and just says 2 to the -3 equals 1 over 2 to the 3. And that is called the negative power rule. B to some negative p is the same thing as 1 over b to the p. The negative just flips where it's at. So b to the negative p was in the numerator, it becomes in the denominator. Likewise, if it's in the denominator, it goes to the numerator. Once you do the flip, that cancels the negative, that gets rid of it. So make sure you don't leave the negative in there. The flipping does the negative power. So for instance, we have 4 to the negative 3, right? This is in the numerator. There's no fraction written, so it's in the numerator. This is the same thing as 1 over 4 cubed, and 4 cubed is just 64. If a power is small enough, it's better to just write the number as is. So 4 cubed is 64. That's pretty small. If it was like 4 to the 8th power, that'd be a very large number. So I would just write 4 to the 8th instead. Okay, here we have 3 to the negative 2. That's in the denominator. That means that it's going to move to the numerator. Now, it's important to note that 7 does not move. That's because 7 does not have a negative in the power. Only 3 does. So 3 moves to the top. Of course, it keeps the same power of 2 in there. 3 squared is 9, and 7 times 9 is 63. That simplifies down to that. Okay, give that rule a try in number 5. Okay, the next two rules are they're kind of the same thing, but just think of it as one idea, that you're distributing powers into powers. So power of a product rule is if you have two things that are multiplying and you have some power on that, that power can get distributed, quote unquote distributed, into the powers, not into the numbers. It's not a times p and b times p. It's a to the power of p and b to the power of p. The same thing applies for division, since multiplication and division are really the same operation. This gets distributed a to the p, b to the p. Now, it also should be noted that if I had something like this instead, a to the m times b to the n, this is the same thing as a power to a power. So we have a to the m times p times b to the n times p. The powers multiply together because it's actually using the power to the power rule, the power rule right here. It's using that idea. Okay. So let's see this in action. One thing I like to do for any kind of expression that has multiple bases is just split it up over each base, just like I did in the previous problem. It just makes it so much simpler what you're looking at. So I'm going to simplify the inside and then do the power at the end of it, at that outside -2. Okay. In the first fraction, I can divide top and bottom by 3. That's going to give me -1/5 times, I have n squared over n to the 4. That's the same thing as n to the 2 minus 4. So it's going to be -2. And then I have m to the 7 over m to the 4. So 7 minus 4 is 3. Now I can distribute the power just like I did using the power of a product rule. I can distribute this power into everything. That's going to give me a -1/5 to -2. In this case, I have negative n squared to the n to the -2 to the -2 power. So it's 2 -2's there. And then m cubed to the -2 power. Okay. Now for this first one, I can distribute this power to the top and bottom. That's going to give me -1 to -2 and 5 to the -2. Then I have a power to a power. I can multiply them. That's going to give me n to the 4th. And then power to a power, multiply them. That's going to give me m to the 6th. -6. Okay, -2 on the -1, that's going to flip it to the bottom. And likewise, the 5 is going to flip to the top. So we get 5 squared over -1 squared times n to the 4, m to the -6. And that just gives us a -1 squared is 1, 5 squared is 25, 25 over 1 is 25. Now, This could be your answer. Normally, we don't like to have negative powers. That's because they're a little bit more confusing to work with. We like to have actual positive exponents. So typically what you're going to see is answers asking for only positive exponents. But either one of these is correct. It's the same expression either way. Okay, give this a try in number 6. Okay, rules of exponents come in handy when using scientific notation. It's a way of writing very large or very small numbers in a much more compact form that really give us the ability to readily see what kind of a number it is. It works like this. So this is a very large number. It's what, 1,000, million, billion, trillion, quadrillion, 638 quadrillion. We just find a decimal point. The decimal point's not written, so it's going to be at the very end of the number. And then we count how many spaces it is before the first non-zero number. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And here, the first non-zero number, first being left to right. So it's going to be right after the 6. So what we get is we get 6.38 times 10 to the power of, how many spaces did we go? We went 17 spaces. And that is scientific notation. It's important to note the decimal point is after the first non-zero digit. It's 6 point something, or 5 point something, 4 point something, 3 point something, 2 point, anything between 1 to 9 can be in that first space. 0 cannot be there. If it is there, you have wrong sign of notation. If you hadn't said 63.8, this is also incorrect because it's not after the first non-zero number. And I left in every non-zero digit. That's because they're what's called significant digits. I'm not going to go into that for much detail. But 6.38, those are all the non-zero digits, so I'm going to leave them in. 10 to the 17 is the magnitude of the number. It's how big the number is. 10 to the 17 is the same thing as, let's see, 100 quadrillion, I guess. It's very large, very, very large. Okay, the same thing can be done for very small numbers. So we're going to count backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9. After the 4, that's the first non-zero digit from left to right. And the negative is still there. It's still part of the answer. And in this case, you see I am writing the 0 because it's between two non-zero numbers. It's 4, 0, 5. If it was 0, 4, 5, that'd be a different case. But if the 0 is in between them, make sure you write the 0. But I'm not writing any other 0 into there. This is going to be times 10, and I said 9 spaces. However, if I wrote 9, this would be a very large number. The number we had is very small, so we write -9. That's because 10 to the -9 is the same thing as 10 to the 1 over 10 to the 9, which is the same thing as 1 over 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you multiply by this number, it makes the number very, very small. And that's what you expect. So very small numbers have negative exponents, where very large numbers have positive exponents. Okay, we've gone from a very large, very small number to sign of notation. Let's go the other way. This is very easy to do. For -9.2 times 10 squared, really all we have to do is multiply this out. 10 squared is the same thing as 10 times 10, which is 100. And -9.2 times 100 is -920. This number is so small, there's really no reason to write it in scientific notation. But it can be helpful to understand how you see small numbers as well as big ones. Okay, 10 to the -6, this tells us this has to be a small number. 10 to the -6, type it in your calculator, you're going to see it's going to give you 0.1, 2, 3, 4, 5 zeros, the 1. And multiplying that, we're going to get 2, 3, 4, 5, 817. Very small number, which is what you would expect. Okay, go ahead and try writing these numbers in scientific notation. Note that this is not in proper scientific notation, so you have to rewrite it. it can help to expand it and then go backwards. All right. Now, for actual arithmetic with the numbers, instead of just writing them out, doing arithmetic, multiplication, and division specifically, it can be helpful to expand the numbers and then do the arithmetic and then rewrite it. It can also be very useful to use rules of exponents, because that'll help speed things along. Now, in this case, this is all just multiplying together. It's multiplication in between. I can rearrange these numbers quite easily. They're all just multiplying together, so there's no reason why I can't do this. Okay, now I have 9 times 3.1, that's going to be 27.9. 10 squared times 10 to the 4, these are like bases multiplying. So we're going to add the exponents. 2 plus 4 is 6. And this is not in correct scientific notation. That's because 27.9 decimal goes after the first non-zero number. So I'm going to expand the number out. That makes it easier for me, so I can never remember how the rule goes. Expand the number, so there's going to be 1, 2, 3, 4, 5, 6. Multiply that together, we're going to get 1, 2, 3, 4, 5. And now I can go backwards. 1, 2, 3, 4, 5, 6, 7. So that's how I like to do it. The main thing here is that if you're going to move the decimal point one space inward, all you have to do is add 1 to the power. That's the rule. But if you can't remember that, just expand the number out and then recondense it. It'll get you the same answer. Division can be done similarly. 6.23 over 7.91 times 10 to the 8 over 10 cubed. Doing that in a on a calculator, let's see, that gives us, okay, I'm gonna have to do an average here. I'm gonna go 3 places because I have 3 digits in the top and bottom numbers. I'm gonna go 0.788. We have like bases that are dividing. 8 divided by 3. Or sorry, 10 to the 8 divided by 10 to the 3. It's gonna be 10 to the 8 minus 3, so 5. Once again, this is not incorrect scientific notation. So let's go ahead and expand it. That's going to give us 78800. Let's see, 1, 2, 3, 4, 5. Yeah, that was correct. And then go backwards 4 spaces. And that's the correct form. So in this case, we needed to move the decimal point 1 space inward. That's the same thing as subtracting 1 from the exponent. That's how the rule goes. Okay, go ahead and try out these ideas in number 9. Okay, if the GDP of a country is $20 trillion, this is the same thing as saying 20 times 10 to the 12, trillion is 10 to the 12. That's why I wrote it this way. But scientific notation says it's 2 times 10 to the 13. That's correct scientific notation. Now, if the GDP of a country is $20 trillion, how much more is it than one with only $200 billion? So we already know what $20 trillion is, right? That's the same thing as 2 times 10 to the 13. And how we can tell how much more it is by dividing. And you'll see why I do that. So $200 billion is the same thing as, so it's going to be 1,000 million billion, 1,000 million billion, $200 billion. So we're going to take a decimal point, get it in scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2 times 10 to the 11. So we're going to divide it by 2 times 10 to the 11. Of course, the 2's cancel, give us just 1, but 1 times anything is the thing itself. So there's really not a reason to write 1. And we have 10 to the 13 over 10 to the 11, like bases that are dividing. Subtract the exponents. 13 minus 11 is 2. This is the same thing as 100. So a GDP of $20 trillion is 100 times as large as one with $200 billion. The reason why I put this problem in here is because sometimes the numbers, trillion, billion, quadrillion, all those things, can seem lost in translation, like you don't understand how big a number is. But in this case, if you're comparing the two countries, then you can see, well, it's 100 times bigger of a number the GDP is. So that's a lot bigger. That's where the helpful thing is of the magnitude of the numbers can shine, really. And here I just have two numbers that are commonly used as scientific notation. We get the mass of an electron. You can see it's incredibly small, 10 to the negative 31 kilograms. Very, very small. And the speed of light, 10 to the 8 miles per hour, or 10 to the 8 meters per second. That's incredibly fast.